Now that we've been introduced to this idea of electrical potential, we want to approach some numerical problems, because ultimately that's how you're going to have to work things on the AP exam. What are the important equations that we're going to be dealing with? One of the most common things you're going to find in many of these problems is going to be a situation in which you have a parallel plate capacitor that is charged, and frequently this will be done by a battery that has some difference in potential or some voltage V. If it's a D-cell battery, V would be equal to 1.5 volts. But V could be any number. The plates are separated by some distance D, and there's an electric field that's within the region of that parallel plate capacitor. There's a relationship between the voltage of the battery, or the difference in potential between the terminals of the battery, the distance between the capacitor plates, and the electric field. This is a special case for the parallel plate capacitor, but it comes up over and over, and so it's an equation that's worth memorizing. The electric field is equal to the voltage of the battery divided by the plate separation. And you'll see that the units that we use for difference in potential or voltage is the unit volt. And the distance D is going to be in meters. So the electric field units can also be expressed as volts per meter. We've seen the electric field equation, F is equal to Q times E, so the electric field is newtons per coulomb, whereas the voltage divided by the distance there, volts per meter and newtons per coulomb, mean the same thing. Perhaps I should have started with the difference in potential and difference in potential energy. There is a potential energy relationship that we should write down. The difference in the electrical potential energy, and now I'm using the subscript Q to represent electrical potential energy, is equal to the charge Q times the difference in potential, delta V. Frequently we're going to see that this difference in electrical potential is going to be the final potential minus the initial potential. So another way that you'll see this written is like this. And now let me make an important note here. And that important note is that when you're dealing with potentials and potential energies, electrical, the signs of the charges are important. That's different than the vectors that we've been dealing with when we talk about electric field and electric forces. When we've dealt with fields and forces, I've encouraged you to draw diagrams and forget about the signs and work with magnitudes of charges. When it comes time to deal with these scalar quantities, the signs are going to be important. And I'm sorry it's like that, but that's just the way it is. So pay attention to signs when you deal with these scalar quantities, because the signs are going to be very important. One more important equation that you're going to come up with has to do with a special case of a point charge. Suppose I have a point charge, capital Q. You don't know if it's positive or negative, you just know that it's a point charge Q, and you're trying to find what is the electrical potential at some point P that's a distance r away from the point charge Q. There's a formula for that. Here's what it is. The electrical potential at point P due to point charge Q is equal to K, that's the electrostatic constant, 9 times 10 to the 9th Newton meters squared per coulomb squared, times Q divided by R, the distance. The sign of capital Q will determine whether you have a positive potential or a negative potential. I'll point out that if you let R go to infinity, the potential at infinity is equal to 0. And normally we refer to that as our reference point, our ground potential, essentially. Let me also make a comment about something you'll hear frequently in these problems, and that is ground, or ground potential. When we get to circuits, we're going to see that there's a circuit symbol for ground. It looks like this. It's a stretch of wire that's connected to a sharp object that's buried into the ground. And when we say something is grounded or something is at ground potential, what we mean is that the low voltage side, the low potential side of that object is at 0 volts. The Brits call this earthing. In the Americans, we refer to it as grounding. But essentially what we mean is that we are taking and providing charge or taking charge away from something until the potential of whatever is connected to the ground is 0 volts. So we're always going to take our potential at ground, or ground potential, to be 0 volts. One more word about units, and then we're going to work the 4 example problems from the textbook. If we go back up here to our equation that relates potential energy, charge, and difference in potential, then we see that the units for potential energy are joules, the units for charge are coulombs, and we define a volt to be a joule per coulomb. So when you come across this unit, volt, then what you're talking about is a joule per coulomb. When we say that something has a difference in potential of 1 volt, what we mean is that it has enough energy to give 1 joule to 1 coulomb of charge. And that's the meaning of volts. Now let's take a look at these numerical problems. A charge of -6 microcoulombs is moved from ground to a point where the potential is plus 75 volts. A. What is the change in the potential energy? B. Is the work done by the electric field in moving the charge positive or negative? And C. How much work is done by the electric field? The formula we're going to use is the change in potential energy is Q times the change in the potential. They tell us that we move the charge from ground, which is 0 volts, to a point where the potential is plus 75 volts. The initial potential is 0, the final potential is plus 75. The difference in potential is going to be the final potential minus the initial potential. And since the final potential is plus 75, the initial is 0, then the difference in potential is plus 75 volts. Remember, signs are important in this. The amount of charge that I'm moving is -6 microcoulombs, or 6 times 10 to the minus 6 coulombs. So the change in the electrical potential energy is going to be that charge times the change in the potential. And now we put the numbers into the calculator. I get that the change in the electrical potential energy is -4.5 times 10 to the minus 4 joules. In other words, when this negative charge was moved through this potential, then the charge lost energy. In particular, it lost electrical potential energy. It may have gained kinetic energy in the process, but whatever happened, it lost electrical potential energy. Now in part B, we're asked about what's happening with the electric field. Now, I don't know what the electric field looks like in this case, but to help me think about the problem, what I'm going to do is draw some electric field lines and show where the voltage would be in this situation. So I want to imagine that these 4 arrows are electric field lines, and to realize that the plus 75 volts is going to be where that a positive charge, a test charge, would have high electrical potential energy. And the 0 volts, the low potential part, is going to be where it has low potential energy. So the 75 volts is going to be to the left side of this diagram, and the 0 volts is going to be to the right side. Now, into this electric field, I'm going to put a negative charge. And that negative charge is going to start at ground potential, 0 volts, and go to the high potential, the plus 75 volts. So when the charge moves in this electric field, the electric field is actually pushing the charge in the direction that the charge is moving. The charge is moving to the left because it starts at 0 volts and goes to plus 75 volts. But that's also the direction that the electric field wants to push the charge. So the charge and the force that's exerted on the charge by the electric field are in the same direction. And so for that reason, I say that the work that's done by the electric field is positive. Now finally, part C. How much work is done by the electric field? Well, what I can say is the work that's done by the field is going to be equal to the change in the electrical potential energy. You could almost think of this as a work energy sort of situation. The work that the field does is equal to the change in the potential energy that occurs in the field. And now I recognize that the work is done as positive, so I'm going to end up with a positive number. It is generally true that the work that's done by the field is equal to the negative of the change in the electrical potential energy. That's a general equation that you can remember anytime. So the amount of work that's done is going to be positive 4.5 times 10 to the minus 4 joules. Another way you could think about this, if you wanted to, is in the work energy theorem. What exerts the force that moves the charge? Well, if I'm exerting the force to move that charge from its initial point to its final point, then I am exerting a non-conservative force. And that non-conservative force, basically, I'm having to push the charge in the opposite direction to the way the charge moves in order to keep the charge from zinging off opposite the direction of the electric field. So I'm exerting a force that is to the left, to the right, while the charge is moving to the left. So that's another way you can think about it. An electron is released from plate A and accelerates towards plate B, acquiring 3.2 times 10 to the minus 15 joules of kinetic energy. A. What is the potential difference between the plates? And B. Which plate has the higher potential? I'm going to answer part B first because I think it's easier. I'm going to look at the fact that this is an electron and realize that if the electron is being accelerated to the right, that means that it's being attracted to plate B and repelled from plate A. So plate B must be positive and plate A must be negative. Let me indicate that on the diagram. B question asks which plate has the higher potential. Now remember, higher potential is defined in terms of positive test charges. And we would say that plate B has a higher potential because a positive test charge would have a higher potential energy if it's closer to B than it is to A. So plate B has the higher potential, plate A has the lower potential. That's the answer to part B. All right, now part A. I have a change in the kinetic energy of 3.2 times 10 to the minus 15 joules. Now, we want to know what is the potential difference between the plate. Where did that kinetic energy come from? Well, it came from the fact that I had some electrical potential energy. So I'm going to say that the change in the electrical potential energy and the change in the kinetic energy are going to be equal in magnitude, and that the kinetic energy is gained as a result of a loss in the electrical potential energy. So the change in the kinetic energy is going to be Q. Q is the charge of the electron. The charge on the electron is negative 1.6 times 10 to the minus 19 coulombs. And now we're trying to find what is the difference in potential. Now I'm going to be kind of sloppy here with signs. The reason is that I know which plate is the high potential and which one is the low potential. So I just want to calculate what is the magnitude of the difference in potential and recognize that the high potential is plate B. So basically what I'm saying is that I'm going to work in magnitudes on both sides of this equation. And now I'm going to say that the change in the kinetic energy divided by the charge is equal to the difference in the potential. And now I know all those numbers, so let me throw them in. Now again, you can see I'm being a little sloppy with the signs, but I can get away with that in this problem because I know which is the higher potential plate. Let me throw in the numbers, and I get that there is a difference in potential of 20,000 volts.